Hello, today's lecture is on optics, solution of problems on optics. Today's lecture is on solutions of problems on optics from S.C. Verma. Seven questions. Page is S.C. Verma, Volume 1, page 381. I have already solved 7 questions in the class, and here I will start solving questions from eighth problem. The problem states, in a Young's double slit experiment, 2 narrow vertical slits placed 0.8 millimeters apart are illuminated by the same source of yellow light of wavelength 589 nanometers. How far are the adjacent bright bands in the interference pattern observed on a screen 2 meters away? It is something like this. Look at this. These are 2 slits, and this is screen here, and this is D, distance between the 2 slits and the screen. Here on the screen you observe the interference pattern, and the distance D between the slits, that is this distance from S1, S2 distance, the distance between the 2 slits is 0.8 millimeters, and distance between the slits and the screen is given to be 2 meters. And then the wavelength of light which is used here, that passes through the 2 slits, and the interference pattern is observed on the screen. Here we have to see that what is the distance between the 2 bright bands. Distance between the 2 bright bands. Between 2 bright bands. That's the question. The light used is here. It passed through the 2 slits, and the interference pattern is observed on the screen. And our question in the problem is that what is the distance between the 2 bright bands? The wavelength used here is given to be 589. If you remember my lectures in the classroom, I have already given you what's the distance between the 2 brights. It is obviously the same as between the 2 dogs. The answer is beta is equal to lambda capital D by small d. That's the answer. You can substitute for lambda, you can substitute for D, you can substitute for small d, and you will get the answer. That is 589 nanometers, of course, into 10 raised to the power minus 9. And there is D 2 meters. And then there is small d, that is 0.8 into 10 raised to the power minus 3. You have to calculate this and you will get the answer. Now let us go to the question number 9. Problem number 9. The problem 9 is like this. Find the angular separation between consecutive bright fringes in the Young's double-slit experiment with blue-green light of wavelength 5 nanometers. The separation between the slits is given to be this. The question is like this. If you have two slits here, and then you have a screen here, and it is distance between the slits and the screen, it is small d. We have to find the two brights, these are the two brights, consecutive brights. We have to find their angular separation. I mean, we have to find this angle. This angle we have to find, delta theta. This is what the question asks, that what is the angular separation between the consecutive two brights. So we have to find this angle. So this d is almost the same as this d, because this d is so far away, then these two distances are to be taken as equal. So it is beta, as you know. So the answer could be directly written as delta theta is equal to beta, that one, by capital D, where beta is fringe width by D. So that is delta theta is equal to, what is beta? That is lambda capital D by small d by capital D. This gets off. So we have answered lambda by D. Both things are given. Here lambda is given to be 500 meters. Lambda is given to be 500 nanometers. So if you substitute it here, and D also you substitute as what you call as 2 into 10 raised to the power minus 3 meters. 2 into 10 raised to the power minus 3 meters. That is 2 millimeters. Substitute D, substitute lambda, you will get the angular separation across beta or across two maxima, two consecutive maxima, or just across beta. That's all. Let me go to the problem number 10. Problem 10 is something like this. A source emitting light of wavelength 480 nanometers and 600 nanometers is used in a double slit experiment. The separation between the slits is this. Interference is observed on the screen 150 centimeters from the slit. Find the linear separation between the first maxima next to the central maximum corresponding to two wavelengths. Here we have two slits, and this is d between the distance between the slits and the screen, and here small d is the distance between the two slits, I mean these two sources, but you are using two wavelengths now. Lambda 1 is two wavelengths are passing, two lights are passing through both the slits. So what are those two wavelengths? That's 480, and lambda 2 is what you call as 600 nanometers. 600, but both in nanometers. The separation between the two slits, that is D is equal to 0.25 millimeters. And then the distance between the slits and the screen is 150 centimeters. You have to convert everything into SI system of units. Find the linear separation between the first maximum next to the central maximum corresponding to wavelengths. Now what he says, we have to find position of the first bright for this, position of the first bright for this. I mean, Y1 we have to find here. We have to find Y1 bar here. So it will be some position Y1 here. Some other position will be possibly somewhere here because lambda is more, so it will be at a higher position, lambda 1 bar. The question is, what is the linear distance between them? That is the question. You will have a pattern for this wavelength, you will have a pattern for this wavelength. There will be first bright corresponding to this wavelength. There will be first bright also corresponding to this wavelength. And then we have to find the linear distance between the two first brights. So I will write y1 is equal to, that is basically y, the position of the nth bright is n lambda d by small d. That is the formula. But here n is 1. So we write lambda 1 d by small d. And what is y1 bar? That is lambda 2 d by d. So the distance between these two brights is delta y. That's okay, y1 dash minus y1, that is d by d, lambda 2 minus lambda 1. You can substitute all the values to get the answer. You have d given, you have capital D given, you have lambda 1 given, you have lambda 2 given. If you substitute all these values, certainly you will get the answer. That's the end of the question. So let me go to the question number 11. The 11th question is, white light is used in Young's double slit experiment. Find the minimum order of the violet fringe which overlaps with the red fringe. The question is something like this. Again, you have two slits here because all the questions are on Young's double slit experiment. And here it is D, here it is small d. Now you are using white light. As you know, white light contains 7 colors. So there will be a colored fringe pattern. Every color will make its own fringe pattern. The question is asked, you have for lambda 400 is for violet and nanometers, of course, and lambda for red is 700 nanometers for red, for violet. The question is, which order of the violet will coincide with which order of the violet will coincide with the red? So there be maybe the 8th of the violet will coincide with some other number of the red. We have to find which order of the violet will coincide with which order of the red, let me suppose. Maybe the 5th of the violet, 5th bright of the violet will coincide with 7th bright of the violet, something like that. So here is the answer. What is the position of the mth bright for violet? Mth bright. So ym is equal to m lambda d by d. Lambda, okay, lambda 1. And what's the position of the nth bright for red? So that is yn is equal to, okay, n lambda 2 d by d. This is the nth bright for red. This is mth bright for violet. If they coincide, then their position should be the same. So ym should be the same as yn because the same position from the center. If they have, then only then they coincide. So here I can write a condition, ym is equal to yn. So I will write m lambda 1 d by d is equal to n lambda 2 d by d. Here this will cancel and it's m lambda 1 is equal to n lambda 2. So it is m lambda 1 is 400 and n and it is 700. This cancels off. So go m times 4 is equal to n times 7. That means 7th that is m by n is equal to 7 by 4. 7 by 4. That means 7th violet coincides with 4th red. That is the answer. 7th violet will coincide with the 4th red. Seventh violet will coincide with the fourth red. That is the answer. So simple. Okay. Let me go to question number, 12th question. The 12th question is, what is the thickness of a plate which will produce a change in optical path equal to the half the wavelength of light passing through it normally? The refractive index of the plate is mu. The question is something like this. If you look at it very carefully, you may have the books with you. This is a plate. Its thickness is T. You pass light perpendicular direction through it. It passes and passes. The question is, what should be the thickness of the plate so that the optical path change caused by the plate is lambda by 2? That's the question. What should be the thickness T of the plate so that this plate can cause the optical path change by lambda by 2? The answer is like this. Had there been no plate here, what would have been the optical path? Simply T into 1. If there was no plate, there would have been some vacuum or even air, but that will be T into 1. Optical path. Now, what is the optical path now when the plate is there? That is mu T. So how much optical path difference change has been introduced or produced by this plate? That is mu T minus T. That is T into mu minus 1. If this optical path change is just lambda by 2, then what should be T? That's lambda by 2 into mu minus 1. That is the answer. So easy. Okay, let me go to number 13 question. Question number 13. The question 13 is, a plate of thickness T made of material of refractive index mu is placed in front of one of the slits in a double slit experiment. Find the change in optical path due to the introduction of the plate. What should be the minimum thickness T, which will make the intensity at the center of the pattern as 0? Wavelength of light used is lambda. Have a look. Now see, again the same pattern of questions. I want to show you as many questions on this so that there's a lot of practice with it. So it is D, it is S1, it is S2, right? Suppose this is a point where both the lights reach. And this is the optical path, S2P is optical path S1P. If somebody asks you what is the optical path change, that is S2P minus S1P. But if I place a plate of thickness T here, and its refractive index is mu, what is the optical path change due to this? Question 1, optical path change. Optical path change. That is the question. Optical path change can be obtained by saying that if there is no plate here, so what is the optical path of this distance, of this little distance? If there is no plate, the optical path is T into 1. If there's no plate like this, the optical path is just T into 1 because there would have been air in place of plate or vacuum. Now, when there is plate here, so what is the optical path within this distance? That is mu T. What is the optical path change now? That is mu T minus T. We just consider only this patch instead of considering the whole two paths. So because the change has been only produced by the plate itself, so we must consider this patch without the plate and the same patch with plate, because the change has been produced only by the plate itself. So it is just T into mu minus 1. That is the answer. But now he says, what should be the minimum thickness What should be the minimum thickness of this plate so that at the center there is a dark, there is what you call as intensity is 0. But that means when the two lights come from the two sources or the two slits, here there must be a path difference of lambda by 2. Only then the darkness will be produced. Only then the intensity will be 0. Only when the path difference between the two path difference of the two light beams reaching here is lambda by 2. So the path difference, actually if there is no plate, the path difference here would be 0 and it will be bright here. But now when you place the plate here, so what should be the path difference created by the plate so that two wave beams reach here have intensity 0? Obviously lambda by 2. By placing a plate here, it should only produce a path difference of lambda by 2 so that now the total path difference is lambda by 2, because without the plate there is no path difference. So delta x is equal to t minus 1, that is the path difference produced by the plate. When they reach here, the path difference should be lambda by 2. And t should be lambda by 2 times mu minus 1. If thickness is this, then obviously when the two light beams reach here at the center, the intensity will be 0. These are a few questions. You just concentrate on them and work them out at your own places. And inshallah, tomorrow I will again explain few more problems from the same book on the same subject.